This brings us to our final video in week 12, which is non-deterministic finite automata. Last lecture, we focused a little bit on the number of states in a DFA needed in order to describe a regular language. However, sometimes you may have two languages that sound kind of similar to each other but require very different numbers of states. So, for example, if you have this regular expression here, it's all strings whose third symbol from the left is 1, and so, third symbol is a 1. And if you want, as an exercise, you can try drawing this DFA. Turns out the minimum size for this is 5. How about this regular expression? It looks like it's about the same length as the other, which is all strings whose third symbol from the right is a 1. Turns out to draw a DFA of this, you need 8 states. And again, if you want to give it a shot, consider trying out. And if you need a hint for drawing the DFA, keep in mind you need to remember what the last 3 symbols are, which means there's 8 possibilities if we're working with the binary alphabet. Now, why is it the case you need more states? Well, it basically has to do with how DFAs work. DFAs always read strings in from left to right, and it's much easier to deal with what's on the left, in other words, making decisions for what's already happened, than to consider what's going to happen in the future. So for the second regular expression, we don't know what could happen if we're at the third last symbol. Is it actually the third last symbol, or is it the fourth last and maybe there's going to be more? Which means that you have to be prepared for every possibility that could happen 3 steps in the future, which is why you need 8 states. So it'd be kind of nice to have a simpler model for this, right? So let me pose to you a hypothetical. Suppose in life, whenever you had a choice, you actually, instead of having to pick right away, could choose both possibilities and see what happens. And at the end, you go back and choose which option was actually best for you. Then you could, decide whom to marry, job to accept, what answer to give on the exam for this course, not necessarily in that order. So here is an NFA, a different kind of state diagram. What's the difference here? Something you'll notice right away is, wait a second, from Q0, if I get a 1, I could go 2 possible ways. I could stick around where I am, or I could go somewhere to a different state. And Q3 over here has no outgoing transitions at all. With our DFAs, we said that would mean it goes to a dead state. With an NFA, things are slightly different here. Basically, scanning in a string gives you multiple possible paths that you could go through, compared to with a DFA, you only have one choice. Hence the term non-deterministic, because suppose that my string starts with a 1, there are some possibilities of where I could end up. Now, for an NFA, we say a string is accepted if one of the possible paths found by scanning through the string reaches an accepting state. Even if there are other paths that lead to rejection states, we ignore all those and just see, can we find a single path that gives us what we want? So this NFA here, which is only 4 states, actually can check if the third last character is a 1. So if in order to have the third last character be a 1, we can have, at the very beginning, any 0s and 1s, the combination doesn't matter, but at some point we need our third last character to be a 1. Once it is, we then could choose to go to Q1, which for the second last character can be anything, taking us to Q2, and for the final character takes us to Q3, where we can reach an accepting state. So let's look at an example scanning in the string 010-110. We start from Q0. If we get a 0, not much choice we have here. We have to stick around where we are. If we get a 1, we have 2 options. We could stay in Q0, or we could go to Q1. When we get the next 0, we either continue to stick around in Q0, or we could go to Q2 at this point, if we had taken the path the first time around. Then we get our next 1, which means we either stick around in Q0, or we go to Q1 now, or if we were at Q2, we go to Q3, and hooray, we've reached an accepting state. However, that's not the whole string, so we're going to have to keep going. Now, if we get another 1, well, previously we were at either Q0, Q1, or Q3. Now, from Q3, we have nowhere to go, so that is going to lead to a dead state, and we just say, okay, we toss that idea out. That's not going to work out. From Q0, if we get a 1, we have options, either sticking around or going to Q1. And from Q1, we could go to Q2. Finally, with our last character, we have a 0, so we can, again, just sit around here in Q0 doing nothing. From Q1, we could go to Q2, or from Q2, we could go to the end. So at the very end of scanning in this whole string, there is one way to reach the accepting state, which is to loop, 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 and then go 1, 1, 0. And because there's one path that works, this string is accepted, even though all the other options lead to failure. So let's go over the formal definition for an NFA. It is a quintuple, just like a DFA, with all of the same parameters. You know, Q is a set of states, sigma is the alpha bit, Q0 is your initial state, F is your accepting states, and delta is your transition function. But there is a difference here. Before, delta would take a state and give you what state you go to if you take an input from there. However, this time, unlike a DFA, instead of just returning the one state you go to, it actually returns a set of possible states that you could end up in. Let's start with the first example. Suppose we have a language. The second last and third last characters of a word are the same, and the alphabet is A's and B's. And we suppose we have to develop an NFA for this language. So let's take a look at what that might look like. So if we need the second last and third last characters to be the same, but everything up till that point doesn't matter, then from the very beginning we should have a loop here that goes through over and over until we have until we decide it's time to move on. I guess I just noticed that there's a C thrown in here. You know, A, B, C. We'll go with this language, I suppose, and we'll toss out the A, B one. Anyway. At some point, we need to figure out what to do with the second and third last characters, and we want them to be the same. So if we want the third last and second last characters to be the same, we need to track them. So at some point, we've decided, okay, we have now reached the third last character, and so it can be either A, B, or C, and each of these lead to different possibilities. So we'll have A, B, and C, all branching off into separate scenarios. Now from there, we need to have the second last character be the same thing. So we're only going to have transitions of the exact same character to go from these states to a state that basically says second last and third last are the same. Now this is not an accepting state because there still needs to be one more character, the last character. So if you end up here and you have to stop, well, that means that this wasn't actually the second or third last characters. They're the last and second last characters, which we don't care about. We only care about the third last and second last. Once we get to here, we then receive the last character, which leads us to our accepting state, the final state that we do want to end up in. Now, something that you may see in NFAs in particular is the idea of an epsilon transition. So a transition where you can take the empty string to go that way. So an epsilon transition is a quote-unquote free movement. If you are in Q0, you can transition to Q1 quote-unquote for free without processing a symbol. For the purpose of a proof, if you have reached Q0, that is the equivalent to having reached Q1, although not vice versa. You can't go the other way. Any NFA that has epsilon transitions can also be called an epsilon NFA, just to denote that, for instance, like the one you can see here, there are some transitions that allow you to go from one to another. Now, let's take a look at this NFA. Does it accept A, B, B, B? We don't really know what this diagram represents, but we're just going to check the characters and see if we can do that. So our initial state is the starting one here, Q0. But that's not actually the real initial state, because by quote-unquote using our free transitions here, we actually could go from Q0 to Q1 before processing any characters, which means our real initial set of states is Q0, Q1, and Q2. Now, in terms of trying to figure out if we can go to a accepting state, well, let's see what happens as we process each character one at a time. So starting from our possible starting states, if we start with the A, where can we end up with? So we could be in any of these. Well, A's don't go anywhere from Q0, so we actually have to start from Q1 or Q2. Q2 can't really take an A, so we're going to have to go from Q1 to Q3. It's the only transition that we can take that actually accepts an A. Although if we are at Q3, we can use the epsilon transition to go back to Q2. So after processing A, our options are we go from Q1 to Q3, so we stop at Q3, or we take from Q1 to Q3 and the epsilon transition ending up in Q2. So our possible transitions, our possible states we could be in are Q3 and Q2. Now we get a B. From Q3, if we get a B, we're in Q4. From Q2, if we get a B, we're in Q5. So Q4, Q5. What if we get another B from there? Well, we just loop. Same for both of them. If we get another B, we loop again. Q5 is a bust. That's not an accepting state, but Q4 is an accepting state. So this NFA accepts the string because there was a path that leads us to where we want to go. So here's a slightly different NFA, but a very close one. What strings are accepted by this? Are AB accepted? BA? Triple B? Two of the above? None of the above? Another practice problem. Consider the language of words from the alphabet AB, where it starts with A, ends with B. For a DFA, you need to have at least 4 states to represent this. But what about an NFA? Can you do it with 2, 3, or do you still need 4? Now let's take a look at how NFAs fit into our discussion of our other topics from the previous 2 weeks. So suppose we have a language over the alphabet sigma. The following are all equivalent. There's a regular expression that matches the language. There is a DFA that accepts that language. There is an NFA and an epsilon NFA that also accept the language. So this leads us into a few algorithms we need to be able to translate from different forms of those equivalencies. First off, if you have an NFA, how do you make a DFA that's the same thing? And the way you do so is using an algorithm called subset construction, where basically you build an equivalent DFA one state at a time. First off, we look at EQ, which is the set of states reachable from the starting state Q by taking 0 or more epsilon transitions. Basically, where are all the places you could start from in your NFA? This will be the quote-unquote name of the state in our DFA. So in our last example where we had you were able to start at Q0, Q1, or Q2, we would name the state Q0, Q1, Q2, and that would be the whole name. The start state of the DFA is ES for the start state of the NFA. So for each state in the DFA, you compute the set of states that you could reach by processing the symbol. And we'll take a look at what this looks like. This process is something we're going to have to repeat over and over until no more states are added. Let's take a look at an example of doing this. So we'll find an equivalent DFA for this NFA where Q0 is the initial state, Q3 is the accepting state. So here is our NFA. And it has, some epsilon transitions and so on. You could draw this out if you want to, but we're just going to work directly from the table actually to figure out what we're doing. Okay, let me move myself out of the way here just for a moment. And we're going to go through the step-by-step process. So first off, let's start at the very beginning. At the very beginning, we start at Q0. Now, what is the actual initial state that we can get to? Because from Q0, we could take an epsilon transition to get to Q3, which means in our DFA that we're constructing to be equivalent, we're going to have a starting state that's named Q0, Q3, because you could be at either one when you start off. Now, let's suppose you're there and you get a 0. Where could you go? If you're at Q3, well, Q3 doesn't have anything, so a 0 doesn't take you anywhere. That's not very helpful. From Q0, you could take the 1 to go to, or it could take the 0 to go to Q1. This is a state we've yet to create for our DFA, so we're going to build a new state and call it Q1. Now, what happens if we get a 1 from Q0, Q3? Well, if we get a 1, we have to go back to Q0, and from Q0, we could take an epsilon transition to get to Q3. So that means that this is going to loop back on itself. Now, so far, that means we have Q0, Q3 going to Q1 and to itself. Well, what happens if we're at Q1 and we get a value? So from Q1, if we get a 0, what happens? Well, it takes us to Q2. However, from Q2, we see there's an epsilon transition that goes back to Q1. So a 0 from Q1 leads us to a new state, the state of either being in Q1 or being in Q2, depending on whether you take the epsilon transition or not. So this is a new state we're going to have to deal with very shortly. But first, what happens if I get a 1 from Q1? Well, according to our table, there's nowhere to go. If you get a 1 and you're at Q1, you're out of luck. So we're going to need a new state. That's our dead state. Presumably from here, if you got a 1 at Q1, that's just going to get rejected. So we're going to make a new state, which is a dead state. From there, all outputs go back to itself, and it never gets accepted. Okay, we still have our Q1, Q2 we need to deal with. So from Q1, Q2, what if we get a 0? Well, from Q1, Q2, if we get a 0, the only option is this one here, which is to go to Q2. And then your epsilon transition can take you back to Q1. So really, you're just looping back on yourself. If you get a 1 from Q1, Q2, where can you go? Well, the only option is to go to Q3. This is a new state that we have not yet gone to. From there, the table gives us nothing. So 0 leads to a dead state, a 1 leads to a dead state. Not super helpful. Let me push myself back up here again. So in our DFA, what states do we end up with? We have Q0, Q3, Q1, Q1, Q2, and Q3, and also this dead state. Our initial state is the Q0, Q3 one, and the accepting states are anything that had Q3 in it, because originally with our NFA, we said Q3 was the accepting state, but you could get to Q3 from the very beginning by just taking that epsilon transition. So we have two options for accepting states, either Q0, Q3, because it includes Q3, or just Q3 itself. So here's the whole summary of what we're going to draw out with our DFA, and I've already gone and done the whole thing for us. So here's our starting state, Q0, Q3. It loops back to itself. 0 takes you to Q1. From there, you can either go to the dead state, which loops to itself, or to Q1, Q2. Here, this loops to itself or goes to Q3. Anything from Q3 goes over to the dead state. And so from here, you can see that we have a complete DFA. Anytime you get a character, it's for sure, you for sure are going to know where it is, and it will lead you to an accepting state if you can get to either the start, if you're either in the starting state or in Q3. So I encourage you to practice this algorithm. I mean, the best way to get good at something like this is for you to try it out. So here is a starting state, here's an accepting state, here's the table. Use the algorithm I just showed you to create an equivalent DFA, and just for extra measure, what is the regular expression that matches this language? Can you figure it out? Give it a try. Now that brings us to our next algorithm. Given a regular expression, can you generate an equivalent NFA? And so the way that you do so is, once again, piece by piece, connecting them with epsilon transitions. And the algorithm for this is called Thompson's construction, I guess named after somebody named Thompson. And so it looks something like this. So here is your automata for the regular expression is just a character. You go from a non-accepting state via the character to an accepting state. How about you have a regular expression A or B? Well, you have your starting state. If you get B or A, it leads you to an accepting state. These, I think, seem pretty intuitive to me, at least. What other possibilities could you have? Well, you could have concatenation. So if you have one character after the other, well, you start from your initial state, you get the A, then you get the B, and that leads you to the accepting state, and that matches AB. How about with a clean star? Well, with a clean star, you usually have a loop of some kind. So in this case, A or B star, in this case, is going to take any combination of A's and B's or the empty string, which means we start at an accepting state. Any A's or B's leave us in the accepting state. So everything here is pretty simple and okay. Now, let's put this into practice. Suppose we have a regular expression, we want to convert it. So here's a simple one, A or B star C. What's this going to look like? Well, first off, we know that we start with that's something that's not accepted. You clearly need to have at least one symbol, otherwise we're not going to be able to do anything here. If we get an A, it is accepted, and we are done. We need to do nothing else. Now, alternatively, we could get some number of B's, but in the end, the thing that does matter we want to keep in mind is, because there's a plus here, we're going to have two different paths that we want to follow. One is just the path where we go A, and one is a path where, since we're doing an NFA, let's use an epsilon transition, and we'll just go a different way and then work on the expression in the other half here. So, epsilon transition over to an alternative path that we can try to take. Now over here, we can get a bunch of B's, as many as we want, so let's make a little loop that loops on B over and over and over, and at some point we should get a C. If we get the C, it should lead to an accepting state. And that's it. Very simple diagram that perfectly represents this regular expression. Now, the real question is, what happens if you need to go backwards? So given an NFA, how do you make an equivalent regular expression? And the way you do so is something called state elimination. So you just saw how we built up a bunch of states to represent the forms of the regular expression. With state elimination, you're doing the reverse, breaking down the states and combining them into terms that you can use, which are regular expressions themselves. So if there's a number of steps to do here. First off, if the initial state has incoming edges, then you need to make a new initial state with an epsilon transition to that state. The reason that you need this is because we want to account for the possibility that you have loops that go through your diagram, and when we're making a regular expression, you want to be able to just say, here is the starting point. So this step allows you to make a quote-unquote real starting initial state, and then the epsilon transition allows you to represent the fact that it goes to the starting state of the NFA. If there are multiple accepting states, or if the accepting state the one accepting state has outgoing edges, you need to make a new accepting state F and make transitions to that, epsilon transitions, from all the former accepting states. That way you can say, this is the end, we have a solid endpoint, and we can condense everything between the starting state that we've built and the end state that we've built. Then we have to eliminate each of the states in between one by one until you only have two states, the initial state and the accepting state. And the transition should only accept one input, but the input itself is going to be a full regular expression. So there are a few strategies we can use to eliminate states based on a few common patterns. First off, if we have two regular expressions that are represented like this, so this should look kind of similar to what we saw earlier with the Thompson's construction. We have one state, then a regular expression, then another state, then a regular expression, then the last state. Well, you can delete the state in the middle by just concatenating the regular expressions on either side. It seems pretty straightforward. How about if you have a loop in the middle? Well, this is a little bit trickier, but we know that we're going to start off with the first regular expression. We're going to end with the third regular expression. In the middle, we can have any number of the regular expression number 2. And when we say we have any number of something, well, that's usually when we apply the clean star. So we can delete K by replacing the transition with R1, R2 clean star, and then R3. Finally, what happens if you have two different ways that you can go to get from one state to another? Well, this is pretty simple. It's just the same as this regular expression or this regular expression, which we represent with the plus sign. So here's a problem we'll go over in the class, which is what should be the first steps for this DFA. Eliminate the dead state, create a new beginning state leading to Q1, create a new final state from Q3 and Q1, create a new final state from Q3, Q1, and a new beginning state into Q1. Let's take a look at an example of generating a regular expression from an NFA. So I picked a rather complicated one here just because I want to make sure that you understand all the steps that you have to go through in order to make this work. So first off, the very initial thing you need to do is take a look and see, does the initial state Q0 have incoming edges? If so, we need a new initial state with an epsilon transition. And here we can see, look, there's an A going into Q0. So we need a new initial state with an epsilon transition. So we'll call that Q4. Epsilon transition goes into our starting state. So by the rules of how NFAs work, anything that our original NFA would accept, this still accepts as well. So we haven't modified it in any sense of that. If there are multiple accepting states, which there are, we're going to need a new accepting state and add transitions to that from all the former ones. So we're going to add Q5 here and put epsilon transitions to that from the other ones. And importantly, these are no longer going to be accepting states, although we're going to delete them anyway, so it doesn't make too big of a difference. Okay, now we're going to, one at a time, start deleting all the states, and as we do so, we need to update all the transitions that occur as we delete the states. So let's start off. We'll do this in numeric order, I think, so we'll start with Q0. But depending on the order you choose to delete these states, you may end up with a slightly different looking regular expression at the end of the day. However, presumably it should still represent the same things that the one we're going to come up with looks like. So first off, we're going to need to get rid of Q0. Well, what happens if we do that? If we do so, we have to look at the possibilities of going from Q4 via Q0 to Q2, the possibilities of going from Q1 to itself, from Q1 to Q2, and not just via this epsilon transition, but also by going A, then through B. So let's look at all of these options here. To get from Q4 to Q2, we take an epsilon and a B. So the concatenation of those is just a B. So we'll have one arrow that takes us Q4 to Q2 via a B. To go from Q4 to Q1, it's an epsilon and then an A. So we're just going to have a transition that's an A. To go from Q1 back to itself, we need two A's. So specifically, there's going to be a loop here that's just double A's. And then finally, to get from Q1 to Q2, right now we could take the epsilon, but there's another path. We can also go A and then B. So we're actually going to take this transition and combine it with that possibility, giving us A, B, or epsilon. And that's going to look something like this. So here is our A transition. Here is our B transition, all from Q4. From Q1, it has the double A loop to itself. And our transition here has changed from being epsilon to epsilon or AB. Now, deleting Q1 is going to make things a little messy, but that's going to end up happening either way. If we delete Q1, where are the outgoing edges we need to consider? Well, the only way that we can go is pretty much to Q2. So we need to consider what are all of the states that go via Q1 to Q2. Well, Q4 does that, and the way it does is by taking any number of double A's, so this is going to be double A with the clean star, and then after it's gotten that, it needs to take either epsilon or AB. So we're going to probably see a transition from Q4 to Q2 that's AA clean star, and then AB or epsilon. To get from Q3 to Q2 via Q1, well, right now we can get to Q2 with just an A, but alternatively we could take any number of double A's, so that's double A star, and then AB or epsilon. And so when we crush things together, it's going to look something like this. So we're going to, rather than having like two arrows that go from Q4 to Q2, we're just going to combine all together. One option is the B, so that's why we see B over here. And the other option is so double A star, and then AB or epsilon. And to get from Q3 over here, we have the original A we could have picked, and then we have double A star, and finally AB or epsilon. And now we can proceed with eliminating some more states. Now, eliminating Q2 is going to mean that we need to think about taking what's here. And so Q4 is going to be able to go to Q3. Q3 via Q2 has two possibilities, either going to Q5 or back to itself. Now let's look at each of these in turn. To go from Q3 to Q, I guess we'll do back to itself first. To go from Q3 back to itself, we need to go this term here, this big block, any number of B's, so this is a B star, and then one more B at the end. And that will allow us to loop back onto itself. So Q3 is going to have a loop that's going to have this block of things, followed by a B star, followed by one more B. To get from Q3 to Q5, well, you have two possibilities. We don't need to worry too much about the loop because we've already got that part covered. We're just going to look at the path that goes from Q3 to Q2 to Q5, which is this term here plus, well, nothing. So we can modify the transition at the top here that normally just has an epsilon transition with epsilon or this block of stuff. Finally, from Q4, we need to be able to get to from Q4 to Q5 or from Q4 to Q3. To get from Q4 to Q5, it's pretty simple. We take this term, we can take B star after that, and then we're just done because an epsilon transition leads us to here. What if we want to go from Q4 to Q3? We take this term here, once again, B star, and then finally a B. And so our transition is going to look like this. So looks a little bit messy. I moved Q3 down a bit, but this is where you have our messy looking loop of ways that we can go through over and over. This one I think I might want to go through just so you can see again how the loop works exactly. But remember, it's this term here, it's A or A star, A, B, or epsilon. So that's A, blah, 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 blah. Pretty much all this stuff, followed by B star, followed by B. So it's the block here, followed by B star, followed by B. To get from Q4 to Q3, you can see we have B, where is it? Yeah, B, like this whole term here, followed by B star, followed by B. And to get from Q4 to Q5, we have this term here, followed by B star, and that's it. We don't need to have the epsilon here. And as I mentioned, from Q3 to Q5, it's the original epsilon transition we had, or the big block of stuff with a B star at the end, because an epsilon transition takes us to Q5. And it leaves us with one more state to get rid of, Q3. The end result of this is kind of messy, and I apologize for that, but not much can be done. So there are in the end, we're going to have two paths we can go through. This one, so one part of our regular expression is just this term here, or we have this block of stuff with a star around it because it loops, and then this block of stuff. So here it is. The first option this block of stuff, closing where I have my red pointer right now, that's like the first part, and then this block of stuff here, all of which has a clean star around it, and then finally the last part. And so this messy looking thing is your regular expression that takes you directly from the starting point to the end point. Now, that may have been overwhelming, but unfortunately, it turns out there's a reason that DFAs and NFAs are really useful, which is so you can not have to very often deal with those messy-looking regular expressions. Now, let's look at a practice example for class. We want to reduce the number of transitions that are in here. Which regular expression can you use to go from Q1 to Q2? AB, A or B star, more than one of the above, or none of the above. So how about this diagram? We want to reduce transitions and we want to go from Q1 to Q3. What regular expression works for that? We'll talk about it. All right, following forward, we want to eliminate another state, Q3 this time. Which regular expression can we write to take us from Q1 to Q4? So at this point, we have the following. What is the final regular expression from the options here? One last practice question. Consider this example. When eliminating Q2, from the finite automata up here, we end up with the one below. Is this correct? Yes? No? Are we missing a transition from Q1 to Q3, or are we missing a transition from Q1 to F? And I'll finish off with an exercise that I think would be worth your time to try out. Looking here, figure out and add in the missing transition in the resulting finite automata after eliminating Q2. Complete the rest of the steps to figure out the final regular expression, which may be messy at the end, but at least when you have it, you'll have completed the algorithm.